Okay, once again, this is Dr. Anthony Bull coming to you from the Exercise Science Department here at Creighton University. Today we're going to be talking about the body composition assessment technique of underwater weighing. And we're going to look at some of the principles used in underwater weighing when we look at the densities of the tissues. Today my helper, the skeleton, is going to be helping me explain how the densities of the different tissues like muscle and the other tissues like fat are going to help us estimate the entire body's composition, or the entire body density. From the body density, we can estimate the body composition, or the percent body fat, which every student loves to know by the end of this class. First of all, let's look at the fat tissue. Fat tissue, not just the fat that's around your organs or on your thighs, but the fat that's everywhere in your body, that's essential for life. All the myelin sheaths, or the Schwann cells that surround your nervous system, those are all made out of fat. Most of your brain is fat. It's a great insulator. Not a great conductor, but a great insulator. And so we use that to insulate our nervous system and help conduct the nervous system impulses a little bit quicker. So fat, not always a bad thing, but to an excessive degree it can be. Fat's density is 0.9 kilograms per liter. So when we look at all the fat tissue together, the density of that tissue is 0.9 kilograms per liter. Now, if we look at the density of our friend the skeleton, plus muscle, plus all the organs in the body, all the fat-free tissue, if we group that all together, it has a density of about 1.1 kilogram per liter. So muscle, 5 pounds of muscle, is more dense and therefore takes up less room than 5 pounds of fat. You can see how the fat model is much bigger than the 5 pounds of muscle model. Each has the same mass, but because fat is less dense, it has a larger volume. So, getting back to the fact that muscle is more dense than fat and has a density of 1.1 kilograms per liter, we can use that and the Archimedes principle that when an object is placed in water, it is buoyed up by a force equal to the volume of water it displaces. What that means is, if we put you in a tank of water, the amount of water you displace from that tank will be equal to the force in kilograms that is buoying you up or making you float. If we put this fat model in a tank of water, it should float. It's less dense than water, because water has a density of about 1 kilograms per liter. It should float. If we put this muscle in a tank, it should sink because its density is greater than water, or 1.1 kilograms per liter. Therefore, if we put your whole body in a tank and you have a lot of lean tissue and some fat tissue, you should sink or float to differing degrees. If we weigh you when you're underwater with all your air blown out, and we compare that weight to your land weight or your land mass, that will give us an idea of how much force is buoying you up. Force in kilograms. That kilograms is equal to the number of liters of volume your body has. So with a few adjustments for air left in your lungs and some air in your GI tract, everybody has it, and the water density, or the temperature of the water and its certain densities, once we make those adjustments, we can estimate your body's volume. If we take your land weight or your body mass divided by your body volume, we get your body density. And from that, we can use a simple regression equation that's been developed on thousands and thousands of people to look at body density versus body volume and estimate your percent fat, or your body composition. We can look at your percent body fat and use that in a number of ways in teaching and in research to help us determine differences in fat or muscle gained or lost. If you start an exercise program where you're exercising and especially doing resistance training, you might gain 5 pounds of this. In the same time, if you reduce your calories and do a lot of aerobic activity, you might lose 5 pounds of this. So you'd lose 5 pounds of this and gain 5 pounds of this, meaning the scale wouldn't say anything different. But if we tested your body composition, we could easily tell the change in the overall body composition. Plus, this burns calories all the time. This just lays around. So if you have more of this, you're going to burn more calories all the time, or your resting metabolic rate is going to be higher. Next time, we're going to look at the actual technique of underwater weighing, where we put you, the subject, the student, in the tank, have you blow out all your air as you go underwater, and we're going to see how much water you displace by looking at how much weight you lose in the water, or how much force is buoying you up in the underwater weighing tank. So until next time, this is me, Dr. Anthony Bull, and my friend the skeleton, saying adios, and we'll see you in the lab.